Okay, so the topic is radiometric dating, all right? Radiometric dating. So we have talked previously, oh, that's not how you spell dating. We've talked previously about a couple of different types of dating mechanism techniques. You remember relative dating versus absolute dating?
Relative dating is around a certain time period. Absolute is till the point of dating.
Yes, so this is an absolute dating technique. And I think I know how to spell technique. T-N-I-Q-U-E, because English wants to be special. English isn't like the other girls. Okay, so radiometric dating is an absolute dating technique. And it is based on Gesundheit. It's based on radioactivity. This is looking really, really ugly. But, you know, that's me. A radioactivity. Oh my gosh, it's so horrendous. But okay. So remember that the difference between absolute dating Remember that absolute dating is like looking at a birth certificate and saying, this is how old something is or someone is. Relative dating is just saying, I am older than you, right? But so are the mountains over there. So it doesn't really give us a very good idea of how much older, right? Okay. Let's see here. Can I do this? Move my camera over here, because this is where my microphone is. We'll see if that works better. I don't know. We'll see. Might not. Maybe will. Probably won't. All right. Okay, so radiometric dating uses radioactivity, right? So we need to understand what radioactivity is. And I'm sure that you've heard this term before, because it's in our everyday speech. Right? Wasn't the spider that bit Spider-Man radioactive? Wasn't that the whole thing? Radioactive spider? What's important for you to understand about radioactivity, is that certain elements decay into other elements or other types of elements, other types of atoms over time. Okay. So certain elements decay into other types of atoms over time. And there's this thing that you see every day in my classroom called the periodic table. No, you don't need to memorize it. You will learn a heck of a lot more about it when you take chemistry from me in a few years. But this is a periodic table. Okay, and these are certain elements. And we'll learn about a couple of them today and how they work in terms of their radioactive materials and so forth. When you hear the term radioactive, you probably think about like how dangerous and scary it can be. Let me just tell you this much. You have radioactive stuff in your body right now. You touch radioactive things all the time. There's radiation coming out of the cement pillars in this room. There's radiation coming from the sky all the time. There's radioactive material in the walls, okay? Radioactivity is not that scary. It's really common, actually. What is dangerous is the amount of radioactivity. If you're close to something that is extremely radioactive, then you're gonna have a bad day. And by a bad day, I mean a bad couple of weeks until you die from radiation poisoning, depending on how radioactive it is, okay? So radioactivity is a way for us, there is a way for us to determine the age of things using radioactivity. So let's talk about a radioactive element really quick. And it's this guy right here, uranium. Uranium is named after the planet Uranus, just like Neptunium is named after Neptune, and plutonium is named after Pluto. Yep. Okay? But uranium is a radioactive material, and you've probably seen the radioactive symbol actually. It's this guy right here. Oh yeah, look at how beautiful. And then it's got a little triangle up here.
Question.
And a triangle right here. Yeah. Question?
There's like there's a different type of calorie, but for like uranium or something?
Calories, as in like the calorie that you can eat. So everything has an amount of calories. But I wouldn't suggest eating uranium. It does have a lot of energy. But anyway, so uranium is really not happy with its life. Sad face. Okay. Uranium is not happy with its life, and it looks at the cool kid, and this cool kid is lead. And for reasons that I don't really want to get into, the atomic symbol for lead is Pb, and it is not peanut butter. No, it's Pb because of the ancient name for lead is plum bum. That also is the reason why plumbers are called plumbers. Because we were really smart and we used to make our plumbing pipes out of lead. Yay. Yes, lead is extremely toxic. And if you get too much of it in your body, you become extremely dumb. So that explains a lot of things. What?
Lead is not the same thing as graphite, though.
Oh, very different. Yes, we call the stuff on your pencil lead because it's just one of those things that people don't know the difference. It's actually graphite, it's carbon. So uranium wants to be lead, okay? It looks over at lead and thinks, man, if I was lead, I'd be so much happier. But then when it actually becomes lead, it realizes that it would have been happy all along if it just accepted itself. I'm just kidding. So uranium wants to be lead, okay? Ooh.
No.
And so when uranium transitions to becoming lead, it does so over a period of time, okay? And that period of time is called a half-life. Half-life. That is a fictitious game that's never coming, my friend. A half-life also can be abbreviated as T half. Oops, half. Okay, the half-life is the amount of time that passes for a radioactive material to decay by half of its mass. And you're thinking, what in the world does that mean? The amount of time, oh, that highlighter function doesn't really work, it just kind of blocks it out. The amount of time that it takes for a radioactive material to decay by half. That's why it's called half-life, right?
Isn't there something like, isn't there something in Chernobyl that's like has a 10 billion year half-life?
Yes, there are.
Like the elephant's foot or something?
There are multiple radioactive materials at Chernobyl, yes, that will not be non-radioactive for a very long time. And this is different for each, oh my goodness, each type of radioactive material. Okay. So for instance, yes, Madison, quickly. For instance, oh, I'll go back, sorry. I didn't give you enough time. I'm sorry, I didn't give you enough time. So for instance, if we look at uranium, which is what we're talking about, the half-life of uranium, is 713 million years. Which I'm abbreviating as just MY. 713 million years is the half-life of uranium. So T 1/2 of uranium is 713 million years. So what that means is, let's say that I have, let's just go with 20. If I have 20 kilograms of uranium, which I promise you that I don't want you to be turning me into the international police. What? In Moab? Yeah, you can find uranium in different places. So 713 million years. So if 20 kilograms of uranium, if we allow 713 million years to pass, how many kilograms would I have after 713 million years? 10 kilograms.
I know.
713 million years later. Okay? We end up with 10 kilograms. Seems legit. Okay, what if we allow another half-life to go by? So another 713 million years. 5 kilograms. Oh, it would be exactly 5 kilograms.
How long would you have to be around 5 kilograms if you before you die?
Well, not very long. So 10 kilograms, 5 kilograms. Then we go 2.5. And then 1.25. So for every 713 million years, we decrease by half. So for every 713 million years, we decrease by half. That is the half-life. That's the whole deal. Okay? So I'm going to move on here. And we're going to do this visually for people. Let's do a circle here. Okay. So we have this circle, and let's say that this circle is, again, our example is uranium. Okay? So after, we'll do the black is the first half-life. Okay? So first half-life. T1. And then we'll do, oh, that's the eraser. Trying to change color here. Blue is going to be the second half-life. Red will be a third. T3. And then finally, we'll do yellow. Let's do green as T4. Okay? So, visually, after 0 half-lives, we still have all of our uranium, right? And none of it is lead. None of it is lead. This is pure uranium. After the first half-life, half of it, look at how beautiful that is. Oh yeah.
That is the best drawing.
I know, I am an artist.
Can I see the drawing?
Nope, nope, absolutely not. I get to do the drawings because I want to make sure that you all know how good I am at art. Okay, so after 1 half-life, we are down to half. Does that make sense, right? We're down to half of our life, okay? After another half-life, after the second half-life, we are down to 1/4. Taylor, I'm really glad that you're verifying that everything seems legit. Makes me feel good about my teaching style. Okay. All right, so we have 1/4 left after 2 half-lives. After 3 half-lives, red, we go 1/2 again. So the pieces of the pie keep on getting smaller and smaller. And then finally, after 4 half-lives, we split this one in half again. Okay, and the original uranium is still right here. So the uranium, so this is half, then 75%, or yeah, 75% is now decayed. And then after that, it's 87.5. And after that, and I'll make a little table for you, and it will be very helpful, at least I think it is. Okay? Questions on how that works? Maybe? No? Yeah, Ricardo, what's up?
Wow. So that would just go on forever, just splitting this house, right?
Yeah, it would go on forever. Eventually, that's a great question. Eventually, the very last uranium atom would become lead.
That's a five.
But it would take a very long time. Remember that the half-life of uranium is 713 million years.
So it would take longer than.
It would take longer than the age of the universe for all of the uranium to decay. Okay, the current age of the universe. The universe is going to keep on going for a very long time.
And the elephant's foot at Chernobyl is still melting with concrete floor base.
Yep. Okay. So I want you to, if you're doing your notes in Google Docs, which I know many of you are, I want you to go to Insert and go to Table. And I want you to do a 3 by 6. Okay? Huh? On paper, you make a table just by drawing it. Okay? And in the top, I want you to put number of half-lives. Let's zoom in a bit here. Number of half-lives. And then I want you to put percentage of radioactive material, radioactive remaining. Okay? And then in your next box, I want you to do percentage of stable. Let's try that again. Of stable material. Okay? So we're going to start off with 0. This one's pretty simple. After 0 half-lives, what will remain of our radioactive material in terms of a percentage? Carl? 100%. Pretty easy. And the stable material will be 0%. Okay? The stable material is the stuff that it decays into. For instance, lead in the example of uranium. Okay? That's pretty simple. 0 half-lives. After 1, this should be another easy answer. How much of the percentage of the radioactive material remains now?
50.
50. Very good, Eli. And of course, we can do math, right? 50. Nah, brah. Nah, brah. After 2, we end up with 25, right? And 75. All right? All right, so if we continue on this pattern, what is the percentage that will remain of the radioactive material?
12.5.
Yes, Eli. It's 12.5. And then the percentage of the stable material that is now in the sample is going to be how many? Oh no, it's math. 87.5. Oh no, how do I subtract 12.5 from 100? So everyone was thinking.
My brain was like, I did the math so weird. I was like, how do I do this?
After
And then
4.
I did 10 plus 5. Then I start new fish brain.
After 4 half-lives, we have 6.25% of the original radioactive material, with 93.75 being stable. Do we see how that works? Sure. I'm going to insert a row because we're gonna do 5.
How would you do that?
You right click, or using a Chromebook, you use 2 fingers to click on it, and then insert row below.
Where?
So you right click and then insert row below right here.
I am smart.
Okay, so after 5 half-lives, we now have 3.125 percentage and 3.125. 96.875. Okay? Ta-da! All right. This will be extremely helpful for you. If you do not have this in your notes, then you're doing the things wrong. Okay? All right. This will be extremely helpful for you because I don't want you to have to calculate this every single time that we're doing a problem. Okay? Truth. Truth. Okay. So that is the, yeah, I'm here. I'm here. Okay. So uranium dating is only one type of radiometric dating. And does it seem all that handy if it takes 713 million years? I mean, what if we want to be more precise? Right?
A lot.
If we want to be more precise, then we need to find something that has a much shorter half-life.
I found something, kind of.
Huh.
I was considering like search for like the Chernobyl elements and stuff.
Uh-huh.
And according to this, ignorant, and this isn't exact, it's rough estimation, but the radiation coming from CS-137 is likely
Cesium-137, uh-huh.
CS-137.
Yeah.
Says it should be about 30 years on that. So life is about 300 years. If it's 10 half-lives.
So, has anyone heard of carbon dating before?
Yeah.
I bet you have.
Last time.
Okay. Carbon-14 is a radioactive isotope. You don't need to know what that means until you take chemistry in 2 years. So carbon-14 is a radioactive isotope of carbon. And it has a half-life that is much shorter than uranium. It has a half-life of 5,730 years. Okay? So 5,730 years. Is the half-life. Half-life. So carbon dating, what it's called, is really handy for understanding things that we want to assign a date to or assign an age to that is much more recent than, 700 million years ago. Okay? So 5,730 years per half-life. So today, well, tomorrow I should warn you, and I'm going to warn you now, we're going to be doing math.
Oh no.
Oh no. Mathematics. All right. So mathematics, as they call it in Britain, maths. So here we need to use some math to figure out some stuff. Okay? So we're going to go through a couple of practice problems, kind of looking at examples of what we might see next class. All right, so I'm going to give you a simple one. Okay? Simple one. So we find a fossil. This fossil has an undetermined age. And we need to figure out how old it is. Well, we can see, so carbon-14, I should probably go back actually really quickly. Carbon-14 decays into, so when we write this C14, decays into nitrogen-14. Okay, so carbon is to uranium. So carbon and uranium are similar that they're radioactive, and nitrogen is stable, kind of like lead is stable. So carbon becomes nitrogen over time. Carbon-14, that is. Okay?
I've done my math wrong, but apparently the current number of times uranium has been half-life is roughly 19.63.
Yeah, sounds about right. So this fossil has a ratio of 75% nitrogen, 14, to 25% carbon, 14. And you need to figure out, knowing that the half-life is 5,730 years per years per half-life, how old is this fossil? Okay? I will. So how do we determine the age of something using carbon dating? Well, the equation is actually quite simple. The equation is number of half-lives, T half, multiplied by the length of each half-life, length of T half, equals age. Okay? Eli.
I did the math because I got excited.
Uh-huh.
And I came up with 37,100 years.
What's that in 14C?
Okay, so Eli, you say that it's how old?
13,700.
13,000?
37,000.
37,000.
37,100 years old.
Okay, how did you get that answer?
I just added it 3 times.
Okay, so why would we do it 3 times?
Oh, I'm an idiot.
No, you're okay. No, it's okay. So the half-life is 5,730 years. So we have this number, right? The length of the half-life. We need to determine how many half-lives it's gone through. If there's 25% of the radioactive material left, looking at your little handy-dandy table that I gave you not too long ago,
I'm doing this.
how many half-lives has it gone through? 2. 2. No, you're okay, Eli. We're all learning this together.
My brain was like, oh, 75, 25, 3.
You're okay. All right. Okay. Do we see how this works? Do you see how this works more or less?
Yep.
Yes? Okay. Let's give you another problem here. This one is just slightly more complex. We're going
Okay, I got the right answer this time.
The correct answer for the age of this is 11,460 years.
Yeah, I got it right this time.
Whoa, years. Okay. Do we see how we did this? We multiplied 2 by 5,300 or 730. Okay. All right. Let's go to another example. This one's just slightly more complex.
We have to write the equations down. Write all that. I think it's very much.
Yeah, I would write down anything that is on here.
I'm just writing down random notes
Yeah, that's fine.
and stuff.
Okay. So this time we're not going to look at percentage. So we find a fossil that has 32 has 32 total grams of stuff that we're measuring, okay? Of those 32 grams, we have 28 grams of nitrogen, nitrogen 14, and 4 grams of carbon 14. So how are we going to do this? How are we going to do this, y'all?
So is it already done? It's like half-life or
So we need to figure out how many half-lives it's been through. Okay? So if it started off with 32 grams of carbon 14,
I think it's
if it started off with 32 grams of carbon 14, it would then go down to how many after one half-life? 16. And then 8.
What are we trying to figure out in this problem, though?
We're trying to figure out how old this thing is.
Oh, okay. And that's all.
Okay? So if it started off with 32 grams of carbon 14 and now it has 4 grams of carbon 14, 0 half-lives, 1 half-life, or sorry, carbon 14. 1 half-life, you go down to 16. After 2 half-lives, it's down to 8. And after 3 half-lives, it is down to 4. Okay? Do we see how that works? Yeah? So how old is it?
It's
3
3 half-lives.
half-lives. Okay, so we have 3 half-lives. Which means it is how old?
How long does half-life is?
Half-life is 5,730.
So it's my original answer, which I forgot. I don't have a calculator, but I'm averaging around.
It is 17,190 years.
You just know that.
Huh?
Why don't we,
How can we know that?
yeah.
Great question. How can we know that? So let's draw our circle again. And this circle is 32 grams. After 0 half-lives, it weighs 32 grams. After 1 half-life, we're down to 16. After another, we're down to 8. And then one more, we're down to 4. 1 half-life, 2 half-lives, 3 half-lives. You see how that worked?
Never had the years.
Huh?
How can we know the years?
Because we know the half-life of carbon. The half-life of carbon is 5,730 years. Huh?
Basically, nothing more.
We're basic, yes, I will tell you what it is, and that's carbon-14. Okay? All right. So we're going to do another practice problem, but it's going to be a little bit different this time again.
My notes are so weird. I hate this.
Why do you hate this?
Because I don't like to math and it's.
Oh my gosh, guys, this is not hard. All right, so again, we are going to use carbon, which is 5,730 years per half-life. Oh, that's a terrible 3. Oh well. Okay, years. All right. So we are looking at a rock that was found next to a fossil that has been dated at 22,000 years old. Twenty-two thousand years old. So this fossil has been dated to be 22,000 years old, and we are trying to figure out what the percentage in this rock that is by it should be. What is percentage of carbon-14 left in this rock? So we know, or at least we think we know the age. So if we did this correctly, then the rock and the fossil should be the same age. Okay, so how are we going to determine the percentage of carbon-14 left? What should it be?
6.25.
So let's look here. Okay, so again, we have this equation. The equation is number of half-lives
No.
multiplied by the length of each half-life. That gives us the age, right? If you do not have this equation in your notes, again, you're doing it wrong. The number of half-lives multiplied by the length of the half-life gives you the age.
What is the?
So we know the half-life, it's this, right? Okay. And we know, we can assume the age is this. Okay? So we need to solve for this and then convert it into a percentage. This is algebra. This is not something that should scare you.
It does, because math is terrifying.
Don't be afraid. Fear not, my young sheep. Yes, you are.
Yes, you are.
All right, shh. Okay. Fear not, my young sheep. How do we solve for this if we have these two? Let me rewrite it. A times B equals Q, because I want to be special. How do we solve for A? Oh, guys, come on.
I thought you were talking about us and we just having to stare
No.
down.
How do we solve for A given this equation?
I think I did it.
This is, come on, guys. This is literally basic algebra.
Yes, and I forget.
Raphael. Oh my goodness. We have a winner.
Just barely.
A equals Q
Oh,
divided by B.
that's a cute. Gosh dang it, it's Lexia. That's not a B.
Do we see this? Do we see how this works?
I see how it works, but Lexia just doesn't want me to see it.
So now that we have this equation figured out, how are we going to determine the number of half-lives? I will go back, Ricardo. Chill yourself. How do I go from a number of half-lives? How do I solve for this given these two? Come on, guys. Eli?
Divide age by the length.
Yeah!
I did that.
So you divide the age by the length of the half-life, which, going back, is 22,000 divided by 5,730. That gives us 0.3, wait, no, that's 2,200. Hello, Mr. Croshaw. 22,000 divided by 5,730. And that gives us 3.83. That is the number of half-lives, which is, I'm going to leave it here. The number of half-lives, which is close to how many full half-lives?
4. I was about to say I really want to round up.
4.
I did math and I got the answer to
Okay? So what percentage should be left after 4 half-lives? And I will give you a hint. It's on your table, Taylor. Eli?
6.25.
6.25.
I've been waiting to say that. for
I know.
15
I
minutes.
know you have. We just had to work it out together. Okay? All right. Last problem, and I'm not going to do this one for you. Raphael. Anybody but me? Anybody? All right. You're going to do this with a person next to you.
I don't have someone next to me. I'm not allowed to look by myself.
Oh my gosh, just relax. Okay. So we have, again, I'm going to write this down for you, 5,730. That is the half-life of carbon-14.
It looks like shadows.
Okay? 5,730. Here's what I need you to do. I need you to determine the age of something that is 5 grams of carbon-14, that has 5 grams of carbon-14 remaining. And there are 75 grams grams of nitrogen 14. Okay, so Eli and Raphael work together.
Can I work on the phone
No.
myself?
Work with a partner. Find someone that is sitting next to you. So let's see here. Michael and Ricardo work with, yeah, you two work together. And then Hayden, if you'll work with Hayden, if you'll work with Aiden, power team. Alexa, if you will just work with Aliana and she'll in front of you. Okay? Everyone else has a partner, yeah? Raphael, wait, let me think here. Ethan, you join Eli and Raphael. Okay? Work together, figure it out. How old is it?
Oh, we're trying to figure out the age. Okay.
Figure out the age. That's where I'm going to end the video for today. Figure it out.
Oh, God.
Katie, work with Katie. Kimberly, work with us together. Madison, work with people. You're humans. You have larynxes. Use them. Speak. You need one. If you need a calculator, I got it.
I still have to figure out how to do the math.
If you need a calculator, I have them up here. And I'm going to tell you right now, you probably need one. I'm gracious. Apparently, no one wants one. I am, when I say that you should work on this and figure out the answer, I am referring to you as an individual person. Yeah, what is it?
28,650.
Nope.
Surprising.
Obviously going really well for everyone.
Everyone's just like, I don't know.
My issue is I did the math right, I just messed something up somewhere.
So you did the math right, but you didn't? Yes, but actually no.
I did the math correctly.
Did you?
Yes.
Yeah.
I know to do, but at the same time, it's like,
Figure it out.
it's 5 times 1, 2, and not so much like
Use a calculator.
no, I have looked it up. I did. Is it adding or is it multiplying?
Okay.
I did something.
Seeing that most of you have said, I don't want to learn this, so I'm not going to even try, let's do it together as a class, shall we?
I tried, but
My issue is I know how it should be done, just not like it.
How big was the original sample of carbon-14? How much was it originally? How big was it?
80.
If you're wondering how I got that, I added these two numbers together.
I did that, and then I combined it into the
Right? Okay? After one half-life, how many grams would it be?
40.
1. After another, how many would it be? 2. After another? 10. 3. And then 5. That is 4 half-lives.
So it's fine.
Okay? 4 half-lives. If we know how many half-lives it's been, how do we take that and figure out the age? Kimberly.
Oh.
Oh my gosh, how come that actually makes sense? We just did that.
It's amazing. It's amazing how it makes sense when the teacher does it.
I got the most basic thing wrong. I'm so frustrated.
You calculated the wrong number of half-lives.
Because I forgot
4
that
times 5,730. 22,990.
I forgot that.
22,920. Do we understand how that works? Yeah? Okay. There will be questions like this on the next exam. We will do an entire assignment based entirely on this next week. I thought we were going to cover more material today. Turns out I was wrong.
I did the math right. I just got the wrong number.
All right. Pack up.
You really like your arm with it. I don't like that. It's right here. Just reach down here.
Most of the year, I didn't have any issue homework because I was online.
Oh, yeah?
I didn't go online. I did some homework. So I'm gonna get it done.
Good.
No, play games. Yeah, outside.
Bye.
Yeah.